So now imagine what would happen if this were a major blood vessel like aorta and this thing bulges all of a sudden like this. In this video we are going to study thin walled pressure vessels. Okay, so we are going to approximate blood vessels as thin walled tubes, pressurized vessels. Use that to study specifically what is known as an abdominal aortic aneurysm. So some of the factors that affect abdominal aortic aneurysm, AAA, or pressure inside the aorta, the diameter of the aorta, the thickness of the aorta, and all that. But there is general consensus that the stress in the aorta is a very good indicator of its health. Okay, and for that reason, we are going to model stress inside an aorta. So we are going to approximate the blood vessel aorta as a cylindrical tube, and let's say there is a pressure P inside the blood vessel, all over the blood vessel. Okay, what we are interested in is the stresses in this tube. Okay, and the specific stress we are interested in is what happens to the stresses along the circumference of the tube. Okay, so this is very important. For example, if you were to burst a cracker, it's always going to split open like this, right? The reason for that is the stresses along the circumference. If you take any particular cross section, the stresses along that direction is usually the highest in the pressurized tube. Okay, for that reason we are going to study those stresses. The way to, of course, study stresses is always take the object of interest and expose the stresses by cutting it open. Okay, so let's say we are splitting it open and expose the stresses. We have the pressure P all over the blood vessel. I'm just showing it here. Similarly, we have, when you cut it open, there are going to be stresses along the circumferential direction. Those are known as hoop stress. Okay, and there will be stresses in this edge as well as stresses in this edge. So they are going to be again all over the entire cross section. So let's look at a very particular cross section in this and analyze force equilibrium. First thing, because we cut it open, there are going to be stresses, right? Sigma h here and sigma h here, and there is going to be pressure all over the blood vessel. To keep the derivation simple, I'm just going to show the pressure over here. Okay, ideally this pressure acts along the surface normal to it. Doesn't matter for this particular derivation. So this is what we have in a particular cross section. Now all of these cross sections need to be in equilibrium. So let's write summation of forces along the y direction in which the forces are acting. Okay, what do we need for that? Let's say the thickness of the vessel is small d. Okay, and the radius of the vessel is r0. So what is the force due to this stress? It's stress times area. So sigma h into d times, let's say, unit L, some length. There are two such edges, so we have a factor of 2. This downward force should be equal to the upward force due to the pressure, P times the area. Area along the cross section is nothing but just this line, which is 2 or not. For a particular length, let's say L, it's going to be 2 or not L. L is common to both. And what we end up getting is the pressure inside the blood vessel is equal to, okay, the thickness of the blood vessel by the radius of the blood vessel times the hoop stress sigma h. Okay. With this, let's go and study a normal pressure vessel. Let's approximate a normal blood vessel using a cylindrical tube, long cylindrical tube. and see what the stresses are and compare it with the blood vessel with an aneurysm. Let's use the maximum pressure during a heartbeat to steady the tube. Okay, that will result in maximum stresses. The maximum pressure should be, let's say, 18 kilopascals. If you convert that into mmHg, you will know why I chose 18. Okay, the thickness of the wall, say, of the aorta, we have been using, say, 2.3 mm. Let's hold on to that. And the radius of aorta should be 25 over 2, let's say 12.5. Okay. With this, we go ahead and calculate what the hoop stress should be using that. Okay. What we should get is close to 100 kPa, 97.8 is what I have. Okay. So now let's study a blood vessel with a aneurysm. Okay. So essentially there is a particular cross section where the diameter is very large. Let's approximate it using a long cylinder. Okay. So pressure, let's say it's 18.3, slightly higher than this pressure. I will explain that in a different video. Okay. So let's hold the thickness constant for the time being, 2.3. Let's say the diameter actually doubles. That's very likely. Okay. So 25 mm is the radius of the aneurysm. So the diameter is 50 mm. Okay. Now these are typical values. If you had to plug in them and find what the hoop stress is, what I have is 199 kilopascals. Okay. So essentially the stresses in an aneurysm are at least twice as large as a normal blood vessel wall. Okay. And based on local geometry and thickness variations, this number could be pretty high. Now let's go ahead and check if these values actually make sense, or at least in the ballpark. Okay. So I'm going to show data from this particular paper. Okay. So you see, normally the stress values are about 100 kPa. Okay. But when there is an aneurysm, the stresses shoot up, can be twice, even sometimes if they are concentrated, could be even 5 times the normal stress values. Okay. So we are in the same order. Okay. Using a very simple model. That's very good. And now I have a couple of questions for you. Okay. This is a normal blood vessel and this is an aneurysm blood vessel. So what happens if this aneurysm is there in a person with hypertension? Okay. So hypertension is high blood pressure. So this particular value is going to be slightly higher. Let's say 20, 22 kilopascals. Okay. Try to see what happens to the stresses in that case. Second, the blood vessels are not like balloons. Okay. The blood vessels are living tissue. They adapt. As soon as they sense a rise in stresses, what they are going to do is they are going to adapt or try to bring down the stresses in some way. The typical manifestation of that is that the thickness of the blood vessels is going to go high. So let's consider a case with an aneurysm. Okay. Now, so the aneurysm diameter is twice as large. Now go and find out the thickness of the vessel wall that would be required in order to keep this value at the normal value, say 97.8. Thanks for watching. I'll see you with another video. I have a couple of balloons, right? All balloons are going to be injured during the making of this video. It's balloon number 2.